Define simple harmonic motion. So simple harmonic motion is when you have the restoring force being directly proportional to displacement from equilibrium and acting in the opposite direction. So that will mean towards equilibrium. You can also define this in terms of acceleration. So acceleration is proportional to the negative of displacement. You can define it either way. A mass on the end of a light spring performs simple harmonic motion. The stiffness K of the spring is 28.5 newtons per meter, and the period of oscillation is 0.42 seconds. Calculate the mass. So the equation that we're using here, time period is equal to 2 pi root m over k. That's the time period for a mass spring system. We're trying to work out what mass is. So let's square both sides of this equation. 4 pi squared, the square root goes away, and then rearrange for m. So bring the k to the top, divide by 4 pi squared. Now we can put everything in. T was 0.42, k was 28.5, and that whole thing is divided by 4 pi squared. Type this in and we get 0.127 kilograms. And then for B part 2, show that omega, the angular frequency of the oscillations, is approximately 15 radians per second. So omega is equal to 2 pi f, frequency is 1 over time period, so you can also write this as 2 pi over t. And we know the time period from the previous question, that was 0.42. So type this in, we get omega is 14.96 radians per second, which is approximately 15 radians per second. The amplitude of the oscillation is 1.3 centimeters. Calculate the maximum speed of the oscillation and the maximum acceleration. So maximum speed, V max, is equal to omega A. Maximum acceleration, A max, is equal to omega squared A. So we know what omega is. From earlier, that was 14.96. The amplitude is equal to, it's 1.3 centimeters, so 0.013 meters. Put both of these things in, we get Vmax to be 0.19. And put that into omega squared A, and then we get acceleration to be, maximum acceleration to be 2.91. Part D. The time of the oscillation starts when the mass is passing the equilibrium position, moving to the right. The position x of the mass at time t is given by this. So whenever we have an oscillator that starts from equilibrium, we use the equation x is equal to a sine omega t. You use sine when it starts from equilibrium because the displacement is 0 to begin with. At what time will the acceleration of the mass first be of maximum magnitude? Alright, so acceleration is equal to minus omega squared x. So then, if we're trying to find when the acceleration is first of maximum magnitude, that would be when displacement is first of maximum magnitude. The graph that we have for displacement looks like this. It's a sine curve. It's first at maximum magnitude over here, a quarter of the way through that cycle. We know the time period in our scenario is 0.42 seconds. We were told that over here, time period of the oscillation is 0.42 seconds. It's the same scenario. So a quarter of the way through the displacement cycle, displacement reaches a maximum value. And because acceleration is proportional to displacement, acceleration will also reach a maximum magnitude a quarter of the way through its cycle. So a quarter of 0.42 is 0.105 seconds. And part 2, calculate a time when the acceleration of the mass is 2.1 meters per second squared to the left. So let's first break down the to the left part of this question. So we're told in the beginning of part D that when the mass starts moving, it passes equilibrium and then goes towards the right. So to begin with, the oscillator is at equilibrium, and just after that, it's to the right of equilibrium. So this is shortly after the oscillator starts. It starts here and then moves towards the right. Our equation for displacement is this: x is equal to a sine omega t, which looks like this. This is a positive sine curve, so that means that soon after we start timing, soon after 0 seconds, x is defined to be positive. If you look at the graph, this region of the graph here, this is just after t is equal to 0, x is positive. So that basically means that if the displacement is towards the right to begin with, and then we can see from our graph that displacement is positive to begin with, that means that the direction towards the right is defined in general to be positive. That's relevant because our acceleration is 2.1 meters per second squared to the left. So that means that acceleration is equal to minus 2.1 meters per second squared. To the left would be negative, to the right is positive. So acceleration is minus 2.1. Now we need to work out time. So acceleration is equal to minus omega squared x. X is equal to this. So let's replace the x that we have here with a sine omega t. We get a is equal to minus omega squared times x, which was a sine omega t. And now we want to solve for t. So let's rearrange for sine first of all. So sine omega t is equal to a over minus omega squared capital A. Let's work out what that is. So the acceleration is minus 2.1. Then we have minus omega squared. Omega was 14.96. We worked that out earlier. The amplitude was this, so that would be 0.013 meters. So times 0.013, and this gives us 0.7218. Now, if we do inverse sine of that 0.7218, we get omega t. So remember that sine omega t is equal to the 0.7218. Inverse sine of the 0.7218 gives us 0.8064, and that would be what omega t is equal to. And then we can divide by omega. So divide by the 14.96, and we end up with 0.054, which is our final answer.